Section 1.62, limits of sequences. We're going to do 3 easy, quick examples, of which I've written down here. Now, the first example, if you just look at it, that looks pretty complicated because if n goes to infinity here, 1 minus, that's 0, 1 minus 0 is 1, 1 minus 1 is 0, so you got 0 on the top. Similarly, you also got 0 on the bottom, so you are nowhere. However, this kind of problem is actually very quick to come out. All you need to do is just do fractions. So let's do some fractions and make this thing come out. We have, on the top, we have 1 minus, I'll write it individually. This is n minus 1 to the power 4, okay? N to the power 4. I'm just splitting up the fractions and the powers. And similarly, on the bottom, we have 1 minus n minus 1 to the cubed divided by n to the power 3. All right? And the next thing we're going to do is, well, fix the fractions. First, we'll do the top term. I'll write down the bottom as n to the power 4 here and solve the whole thing, which is n to the power 4 minus n minus 1 to the power 4. That's just the numerator. And then next, we're going to do the denominator. And as you can see, it looks very similar to the numerator. But since we're dividing, we're going to flip it around and multiply. Okay, flip and multiply gives us similarly to this, so n3 minus n minus 1 to the power 3. So that's that. Now, and at this point, you notice that the fourth power and the third power cancels out, so we have just 1 over n left. And then the rest of it, we have 1 on the numerator and 1 on the denominator. And we just need to calculate out what that is. This is n to the power 4th. Now remember the binomial expansion, which says if you have 1 plus, actually let's put it another way, since ours look different. If you have a plus 1, okay, to the power m, let's say, then the answer is equal to a to the m plus m times a to the power m minus 1 plus other stuff that we don't care about right now. So this subtraction is equal to n times 4th minus n to the power 4th. That's gone. And then the next term is based on here is 4n to the power 3. 4n to the power 3. And because of the minus sign, this is a negative value. However, being that there's another negative sign there, we end up having a positive. Now, similarly, we have this one. Again, the n3, subtract out the n3 in here, and so then all we have is the negative 3n squared. Right here, the second term, okay, which is n minus 1. And then, of course, there's another minus sign there, so that's positive again. So, but that's just the first term. There's other stuff that we haven't done. The reason we don't do it is because we don't care what it is, because those terms are going to be lower powers. And we only care about the highest powers, which is 3 on top and 2 on the bottom. And as you can notice, there's another n here. So the whole thing is going to be the same powers. Okay, you have n3 top and n3 on the bottom. So it evens out. So as n goes to infinity, this limit only goes to 4/3, which is very interesting because that's the power right here, and that's what dominates this problem. So, and you end up being the entire thing will go to 4/3. The next problem we're going to look at is a very similar problem. This thing, if you subtract it, this goes to 0. This thing goes to infinity, so you have infinity times 0, which is nowhere. So how are we going to do that? Well, we're going to pull another trick. Anytime you see these things, square roots, then you try to do rationalizing. For no real reason, it's just see if it gets you anywhere. So let's rationalize this thing. To rationalize it, we have square root of n divided by the plus sign. Okay, to rationalize, we'll multiply and divide by the plus 1 and plus square root of n. And then the top then becomes the minus times the plus becomes difference of squares, so that you just have n plus 1 minus n. And that, of course, is just 1. So what we have after rationalizing is this. Square root of n plus 1 plus square root of n. Okay, so in rationalizing, we end up with something in the denominator. And then so where does that get us? Well, it actually comes in very nice and handy because this value, which I will write this in the middle here, square root of n plus 1 plus square root of n, this value is going to be bigger than this thing right here. N over n plus 1 and another n plus 1. What I have done is simply replace this term with n plus 1. And being that n plus 1 is slightly bigger than this, then the fraction is going to be, the whole fraction is going to be slightly smaller than this term. Now similarly, we're going to do the other side, this. N plus square root of n. And the reason is because I reduced this value by 1, so it's just now square root of n. And being that this is smaller in the denominator, the whole term becomes bigger. Now what is this? If you look at this, this is simply 1 over 2. Just this chunk. Okay, that's just 1 over 2. And also, now this one, if you calculate it, then this one equals to, this term right here, equals to 1 over 2 square root of n over n plus 1. Now that, where does this go? This n over n plus 1 goes to 1 as n goes to infinity. The square root of it also goes to 1, so this whole thing has to go to 1/2. And that means, now notice this is 1/2, this goes to 1/2. Therefore, the middle term by the squeeze theorem or principle, the middle one must therefore also go to 1/2 as n goes to infinity. That finishes our second problem. Now let's look at the third one. The third easy problem says, if the limit, if we know this, okay, we already know this, we're not trying to prove it. If this is true, that is the limit of xn minus x over xn plus x, it happened to be 0, then the limit of xn will actually go to x. Now to prove that, we're going to pull another trick. That is a very simple one. We'll set yn equal to this stuff, xn minus x over xn plus x. Okay, now if that is true, then as given, the limit of yn is 0. Okay, as n goes to infinity. So then what? Then we're going to do fractions. Again, we're going to isolate xn out of this mess. So to isolate xn, we multiply both sides. So we have xn yn plus xyn equal to xn minus x. And then from there, we will isolate xn equal to, first we'll do the stuff that doesn't have xn, which is move this over, minus x yn minus x divided by, okay, this is yn, and then this is minus 1. Okay, if you move this over, so it becomes yn minus 1. So then, and then at this point, we say, since yn goes to 0, so yn goes to 0 as n goes to 0. As n goes to infinity, okay, yn goes to 0. So this and this disappears. Then xn, it goes to negative x over negative 1, which is just x. Therefore, the limit of xn goes to x, as is we're supposed to prove.